Hi guys, this video is an irreducible polynomial of an algebraic number. Let E be an extension field of F, F is also a field, and alpha of E be algebraic over F. In this theorem, it guarantees an irreducible polynomial in Fx with 0 is alpha. It states, then there exists an irreducible polynomial Px in Fx such that P alpha equals to 0. That means alpha is a 0 of the polynomial Px. And also, this polynomial Px is uniquely determined up to a constant factor in F. That means this polynomial Px is unique except for the constant factors. And also, this polynomial Px is of minimum degree in Fx having alpha as its 0. That means of all the polynomials in Fx with 0 is alpha, Px is of minimum degree. And so, if f alpha equals to 0 for Fx in Fx, that means if alpha is a 0 of Fx, then the polynomial Px divides Fx, and this irreducible polynomial Px is denoted by this symbol irreducible alpha f. Now let me explain what this theorem means. The field of complex number is an extension field to the field of real numbers, and the imaginary unit I belongs to C is algebraic over R. The polynomial Px equals to x squared plus 1 in Rx is irreducible in R, it cannot be factored in R, and I is a 0 of Px, so Pi equals to 0. So there exists a polynomial Px which is irreducible in Rx with 0 is I. Second, we have 2 times x squared plus 1 or any number k times x squared plus 1. These two polynomials are same except for the constant factors 2 and k. So the polynomial Px is unique except for the constant factors. Third, we have fx equals to x to the power 4 minus 1, f of I equals to 0. This shows I is also a 0 of fx. X to the power 4 equals to x squared plus 1 times x squared minus 1. So fx equals to px times x squared minus 1, and this shows px divides fx. So any polynomial with 0 is also I, then px divides that polynomial. Fourth, we have Px whose coefficient of x squared is 1 is called monic. The polynomial 2 times x squared plus 1 coefficient of x squared is not 1, so this polynomial is not called monic. Now we proceed to the proof. First, phi alpha from fx to E is the evaluation homomorphism. Then kernel of phi alpha is an idol of fx, and any idol of fx is a principal idol. So kernel of phi alpha is also a principal idol. So kernel of phi alpha is generated by a polynomial Px in Fx. K phi alpha equals to an idol generated by the polynomial Px. Second, we have the polynomial Px is of minimum degree because it is a generator of the idol kernel phi alpha. Third, we have f alpha equals to 0 for some fx in Fx. That means the polynomial Fx is any polynomial in Fx with 0 is also alpha. Then f alpha equals to 0 means f alpha equals to 0. 0 is the identity element, so Fx must belong to kernel phi alpha. So Fx belongs to the idol generated by Px, so the polynomial Px must divide Fx. This also shows that Px is of minimum degree with 0 is alpha, because for any polynomial Fx with 0 is also alpha, Px divides Fx. So Px must be of minimum degree with 0 is alpha. Fourth, we have if degree of any polynomial gx equals to degree of the polynomial Px, then we must have gx equals to a times Px for a belongs to F, a is a constant. So this polynomial Px, it is uniquely determined up to a constant factor. So now it only remains to show the polynomial Px is irreducible. Let Px equals to Rx Sx, that is the polynomial Px is reducible if possible, where the polynomials R and S belongs to Fx. Then we observe that the degree of R and S is less than that of P, clearly. Second, we have P alpha equals to 0, and this implies R alpha S alpha, the product equals to 0. And this implies either R alpha equals to 0 or S alpha equals to 0 because Fx is an integral domain. Because R alpha equals to 0, S alpha equals to 0, the polynomials Rx and Sx, they map with 0, the identity element, they must belong to kernel phi alpha. But which is a contradiction, because the polynomial Px is of minimum degree to be on the kernel phi alpha. So the polynomial Rx and Sx cannot be on the kernel phi alpha because their degree is less than that of P. This shows the polynomial Px is not reducible and the theorem is proved.